Good morning. Welcome to week 2 of Unit 8. We're going to learn the alternating series test today. I got a video message from Edward over the weekend, and he made a video of himself reacting to our Happy New Year wishes. And so I think on block day we'll have enough time to look at that video, but for today we need to get right down to business. Were there any questions on the homework that was due today? 8.4, direct comparison and limit comparison. Now is a great time to ask. Anything that was unclear? Looks like we're good to go. So we're going to jump into the new material. 8.5 is the alternating series test. And this one works in conjunction with the nth term test. Perhaps you recall that the nth term test is incapable of detecting convergence. And so there's a big X right through here in our chart. Well, in complementary fashion, turns out that the alternating series test is incapable of detecting divergence. So what happens is when you get an alternating series that doesn't satisfy the conditions for convergence, then we're going to go to the nth term test and use the nth term test on alternating series in order to confirm that they diverge. So 1 and 8 work as companions. So here we go. Let's take a look at the alternating series test. There's a couple of different ways to write out the 3 conditions. And this might look a little bit different in the book, but mathematically it's identical to what's in the book. Notice that you take, for the alternating series, we're going to view it as our a sub n is going to be separate from the alternating part. So let's just cross this out. It's going to be sigma -1 to the n a sub n. So we're going to analyze the a sub n separately from the alternating factor. Sometimes it'll be -1 to the n plus 1 or n minus 1, but the -1 to the n or n plus 1 factor is what makes the series alternate between positive and negative or vice versa. Sometimes it won't actually be in that form. Sometimes it'll be in a form like sigma sine of pi over 2 plus pi n. Pi over 2 plus pi n, which does not obviously alternate until you start putting in some values of n. I mean, think about it. Sine of pi over 2, sine of 3 pi over 2, sine of 5 pi over 2. I mean, these values, sine of pi over 2 is 1. Sine of 3 pi over 2 is -1. Sine of 5 pi over 2 is +1. It just alternates between positive and negative. So instead of putting a very obviously alternating factor like -1 to the n, they'll put in something a little more cryptic, something like sine of the quantity pi over 2 plus pi n. So watch out for that. But either way, you've got to analyze a sub n. It's got to meet 3 conditions. A sub n has got to be greater than 0. So far, it's just like the integral test. So the integral test was a sub n has got to be greater than 0. 2, a sub n is non-increasing. This looks and seems ever so similar to what we had in the integral test. Pretty darn convenient. Positive, decreasing, continuous. A sub n is decreasing is what we had up here. Here it's almost the same thing. Non-increasing is not the same thing as decreasing. If the terms in the series go 5, 5, 5, 5, 5, they're not decreasing, but they are non-increasing. And so there's a little bit of a difference here, but so far, the reason I use this sequence of conditions is because it's so similar to the integral test. And up here, number 3 was a sub n is continuous. Here, it's going to be the limit as n approaches infinity of a sub n is 0. Those are the three conditions. If you do not meet those three conditions, then go to the nth term test in order to show that the alternating series diverges. So if you can't meet these three, then just switch up to the nth term test and go from there. Let's practice using this. I have a picture for you. This is actually a pretty important picture for the Unit 8 test. And I'll just give you a heads up. This diagram will be on the Unit 8 test. It might be a different function, but you're going to have to be able to look at a graph of a sequence of partial sums. Okay, here we have this is probably the second most famous series of all series. The most famous series is the harmonic series. This is the alternating harmonic series. Take a look at what this thing does when you put the initial value of the index of summation in for n, -1 to the 1 plus 1, that's -1 squared, 1. Instead of 1 plus a half plus a third, it's 1 minus a half plus a third minus 1/4. I want you to write plus 1/5 all the way up to plus 1/7, minus 1/6 plus 1/7, and then we use the symbol minus plus dot dot dot. The minus plus indicates that the alternating pattern, the pattern that alternates between positive and negative, continues. Okay, so what we're going to look at today is not only how to do the alternating series test, which is actually the easiest part of the lesson. In fact, maybe we can just do an example of that real quick. Alternating series, in terms of just using the test, let's just go all the way to this example right here. This is a very small part of the lesson. But this is an alternating series. Let's see how it fares according to the alternating series test. How many terms are required? Notice that the directions do not say determine whether it converges or diverges. But let's just, we're going to do some other things with this example, but let's just take this example as an opportunity to practice using the alternating series test. So we'll make it kind of small and put it off to the side. A lot of other things you want to do with that problem, but here's how you would run the test. You would say a sub n equals 1 over n cubed minus 2. Notice a sub n does not include the alternating factor. All we look at is the part that's not alternating. And then we write alternating series and underline it to indicate we're going to run the alternating series test. Step 1, a sub n is greater than 0. Check. For all n values 2 on up, that's true. 2. Pretty darn convenient. It's not decreasing, but it's close. A sub n is non-increasing. Check. Look, the denominator keeps getting bigger. This thing is actually decreasing. And number 3, the limit as n approaches infinity of a sub n equals 0. Check. And I've run out of room here, so I'm going to wrap around to the top. Therefore, series -1 to the n a sub n converges. Notice it's not as simple as writing series a sub n, because this series is more than just a sub n. It's -1 to the n times a sub n. So that's really a small part of today's lesson, is using the alternating series test. A much bigger part of today's lesson is approximating the value of an alternating series to a certain allowed error. And this is where that story I told you about Mr. Luz, Shakar Luz's father, he came in and he was trying to figure out how many terms do I need so that the approximation of the sine curve is close enough to the actual sine curve so that I'm within the quality requirements at Motorola. We're going to learn later on in our study of series that sine x is an alternating series. Sine x is x minus x cubed over 3 factorial. We saw this on the first day of the unit. We compared sine x to the polynomial x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus minus dot 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 forever. Today we're going to address questions such as how many terms in an alternating series are required to approximate the series to within a certain allowed error. So, to give you an idea of how that's going to happen, we're going to take a partial sum as the approximation for S. So please define S as the value of the series. It's an infinite series. So just put an S out there, and we could approximate S with the first partial sum, the second partial sum. But I want you to, first of all, look at what happens in terms of vocabulary. If we decide that the first 5 terms is enough, we're going to use S5 as our approximation. So let's bracket that out. We haven't decided yet how we know that 5 terms is enough, but suppose we've decided that 5 terms is enough. Well, there's vocabulary for this term right here, the last term that we keep. And there's also vocabulary that we need to learn for the first term that we throw away. This is called A sub k, where k stands for kept. This is the last kept term. And the next term is A sub t, where t stands for throwaway. This is the first throwaway term. So, working a little bit on vocabulary here. The first term is 1, and you can represent the ordered pair 1, comma 1. This is in the form n, comma s sub n. The first partial sum is 1, so it's plotted right here at 1, comma 1. So the length of this line segment happens to also be the numeric value of the first term. Now imagine this point as the ordered pair 2, comma s sub 2. This is the second partial sum. It's really 1 minus a half. The second partial sum is 1/2, and notice that this would be that value, but just want to show you this line segment right here. This line segment is the absolute value of negative 1/2. The length of this line segment is the absolute value of the second term. And so here we have 1, add minus a half. Now we're here at the second partial sum. So label this S2. Up here, this guy, that's labeled S1. First partial sum, second partial sum. The third partial sum is the sum of the first 3 terms. 1 minus a half plus a third. That brings us up to, let's see, 6, 6 minus 3, 6 is 3, 6. So this is 5, 6 right here. This is 0.3, comma 5, 6. We'll call that S3, the third partial sum. And would you draw a line segment whose length is exactly 1/3, just to see if you're interpreting this diagram correctly? Call this segment AB, had a length of exactly 1/2. Draw a line segment CD, whose length is exactly 1/3. Okay, I'm going to do it in blue. When you're done, you can look up here. CD. Notice how the third partial sum is found by taking the second partial sum and adding the third term, which is the absolute value of 1/3. Raise your hand if this is where you drew line segment CD. Okay, good. Any questions on how to locate segment CD? Okay, now I want to get a line segment whose length is exactly 1/4. Would you please label S4 and draw in a line segment whose length is exactly 1/4, which is the absolute value of the fourth term? change the first one to red, we're going red, plus orange gets me to S2, plus blue gets me up to S3, and I'm gonna go to green, and we'll call it segment EF. Who'd like to come up here and draw a segment EF, whose length happens to be exactly 1/4? Let's take a volunteer. Maybe while you're up here, you can even say hi to Edward. Is there a volunteer who'd like to come up here and draw a line segment labeled segment EF, whose length is exactly 1/4? So far we've taken 1 minus 1/2 plus 1/3 to get to S3. This line segment, Moose, do you want to come up? You want to try it? No? Okay. Who would like to? All right, Gwyneth, do you want to come up? Here, we'll put it into, that's okay, if you don't get it, I'll talk you through it. But basically, it's got to take us from the third partial sum to the fourth partial sum. Go ahead and tell me where you think it might be. And, oh, you know what? Sorry about that. Go ahead and label and select the pen tool. I should have had this selected for you, but go ahead and click right here. Now you're in pen, and go ahead and select green. All right, now, let's go with segment EF and label those endpoints. All right, thank you. So, yeah, that's right. You can think of some motion in this. We've got, I'm just gonna make this first one red. So visually, there's motion in this diagram. It's like we're going from 0 up to the first partial sum. And then from the first partial sum, we go, since it's minus 1/2, we go down 1/2 to get to S2. And then we go up 1/3 to get to S3. And then we come down 1/4 to get to S4. So this should be labeled S4. GH. Go ahead and draw a line segment GH, which has length 1/5. It takes us from S4 to S5. Up 1/3, down 1/4. Let's go up 1/5. So when you're done, you can look up here, see if we agree. Change that to purple. Okay, so we're going to go green because that's color coded with the 1/5 up here. The 1/5 circled in green is going to match with segments. Put it over here. Laterally, it doesn't matter where you locate these line segments. What matters is the vertical displacement. Okay, so hopefully you see that segment GH, which has a length of 1/5, goes up and takes us home to our approximation. Suppose the authorities at Motorola said we want to use the fifth partial sum to approximate S. S is approximately this. Now, as you can see, it just keeps going. It approximates to about, I think it's natural log 2 is where it ends up. Let's type that into the calculator. I don't know if my memory is serving me correctly on that or not. It's been a while, but natural log 2.69. Again, it looks like that's about 0.69. But this is, this horizontal line right here is the true sum. We'll call it capital S. This horizontal line is y equals S, the true sum. So, so now we see visually what's called the remainder. And there's a very important visualization here. There's an infinite number of terms here that we're throwing away. The first throwaway term is 1/6, which ends up going negative. But really, if we're going to keep the first 5 terms, then we throw away an infinite number of terms. It's called the remainder, or the actual error. And there's some very important line segments here that we need to put on here. First of all, let's put in the line segment that has length 1/6. The two most important ones here, there's actually three that we're going to analyze, but and we're going to put them in the blanks here. First one is less than the second one is less than the third one here. But we've got 1/5. We also need to look at 1/6, which is the first throwaway term. Notice down here in orange is S6. First throwaway term is 1/6, and that takes us in orange from S5 down past the truth to S6, E, F, G, H, I, J. So segment IJ has a length of what? Raise your hand if you're reasonably sure you know the length of segment IJ. Actually, I'm sure all of you do, so just call it out when I say class. What is the length of segment IJ? Class?
1/6.
That's 1/6. That's the length of the first throwaway term. So, that takes us down to the sixth partial sum. So here we go. We're going to match each word or phrase in the series above, described in words. Okay, so the error. The actual error is, in words, that's self-explanatory. The error is the difference between our approximation, S5, and the truth. So let's put a line segment here for that. We're going to go in black for that. The error is KL. The length of segment KL is what we mean by the error. It's the difference between our approximation and the truth. We're off by exactly KL. In fact, if you add up all the terms that we're throwing away, they would add up to be exactly KL. That's an infinite series. The error, -1/6 plus 1/7 minus 1/8 plus ... forever, gives us the length of segment KL. All the terms we throw away are the difference between our approximation and the truth. That's what we mean by the actual error. Okay, so analytically, we can come up with an algebraic expression for that. It's the absolute value of S minus S sub n. It's the difference between the truth and the partial sum that we've selected. In our case, it was S sub 5. So in general, it's the nth partial sum, but you know what? I'm going to make it S sub 5 because in our example, we're all about pleasing the authority figures by picking the fifth partial sum. So the difference between the truth and the fifth partial sum is the error. Numerically, what is it? Numerically, it's the summation from n equals 6 to infinity of -1 to the n plus 1 over n. -1 to the n plus 1 over n. If you wanted the number, it would be that, I could have also written that, maybe it would have taken up less space. If in the numeric column, I would have written -1/6 plus 1/7 minus 1/8 plus 1/9 minus plus ... forever. But that's what we mean by the error. Okay, the remainder is synonymous with, it's just another term that's used for the error. So in words, we call it the error. It's the same all the way across. The remainder and the error are synonyms. You're just responsible. Sometimes I'll ask you for the remainder, sometimes I'll ask you for the actual error. The first term of the remainder. So we have actually a line segment that lines up the first term of the remainder. It takes us from S5, so that was segment HG, so segment GH. So the first term of the remainder is segment GH. And analytically, it's the absolute value of A sub 6. It's also known as the first throwaway term. So far we have a pattern going here. We've got two expressions for segment KL. Segment GH is sometimes called the first term of the remainder, sometimes called the first throwaway term, same thing. Numerically, it is 1/6. Okay, so the last term that we kept was, in this case, 1/5. And the line segment for 1/5 was, oh yeah, okay, I can tell you're wondering about GH. You're right, GH, that was after, that was oh, well, no, hold on. GH was 1/5. Yep, so that needs to be corrected. Let's correct the GH. And it should be instead, yep, the 1/5, 1 minus half plus a third minus a fourth plus 1/5, so it should be IJ. Let's make that IJ instead, because that's the one that's 1/6. Okay, so the last kept term was GH. So I'm going to make that one green. GH is the last kept term. And that's for item 5. So item 5 comes across at GH. It's the absolute value of the 5th term. It has a numeric value of 1/5. Okay? Now for the maximum error. What the inequality that we're going to work on, the whole point of this page is to understand something very important, that is that the actual error, which is very difficult to get a handle on because the actual error is an infinite series. So what we're going to do is we're going to notice that the actual error is always less than something that we call the maximum error. And as long as we keep the maximum error less than the allowed error, which is up to the executives at Motorola, they get to decide what's allowed. And so we need to ensure that the actual error is less than the allowed error. So it turns out that in this diagram, we're going to be able to see something called the maximum error. And as long as we keep the maximum error less than the allowed error, as long as we keep the maximum error less than the allowed error, then the actual error will be way less than the allowed error, and the authorities will be super happy. So here's how we're going to pull this off. We're up to item 6, the maximum error. This is all focusing on the maximum error. The maximum error is synonymous with the first throwaway term. See it in the diagram. Maximum error is the same thing as the first throwaway term. And by maximum error, that means an upper bound on the error. So 6 and 7 are synonymous. They mean the same thing as first throwaway term. So 4, 6, and 7 are all the same concept. Let's find out why. An upper bound on the error. Take a look at it. I actually have it in, I have it in orange. So if we want to try to color code this, take a look at the first throwaway term of 1/6. If you're going to look up here for anything, look at this. Look at the connection or the comparison between the orange line segment and the black line segment. The orange line segment, the first throwaway term, has a length of 1/6. Notice how that's bigger than the actual error. Orange is longer than black. So what we do, our strategy is going to be, let's just color code this. The maximum error is the first throwaway term, so we're going to make that orange. We don't know the actual error, it's a sum of an infinite series, but the actual error in the diagram is black. And so maximum error. Then the allowed error is decided on by the authority figures. I'm going to make that light blue. So the authority figures decide. So the executives come in and say, well, you're allowed this much error. Maybe it'll be 1/1000th. So our strategy is going to be able to find the first throwaway term that's less than the allowed error. Because if this number right here, if the first term that we don't use is less than the allowed error, then the actual error will be way less than the allowed error. Now, we don't have a line segment for the allowed error up here, but suppose that the allowed error were something like this in teal. Suppose they say, we'll allow you this much error. Maybe this is 1/1000th. So as long as you find a throwaway term that's less than the allowed error, then the actual error will be way less than the allowed error. If orange is less than teal, if orange is shorter than teal, then black will be way shorter than teal. That's the thinking behind finding what number of terms is needed to approximate a series. So in terms of vocabulary, just do an example here. How many terms are required for the error of the remainder to be less than 0.02? Suppose that the executives come in and say, we'll allow you to be off by 0.02. It's more common for them to pick 0.001, but suppose they give you an allowed error of 0.02. So here's how you're going to handle this. You're going to define t as a subscript of the first throwaway term, or the first term of the remainder, but t is for throwaway. And we're going to declare that with the word let. So we're going to say let t represent the subscript of the first throwaway term. We're going to have to say let k represent the subscript of the last kept term. We're also going to have a sub n defined as the non-alternating part, which is 1/n. A sub n is 1/n. So what we're going to do, in keeping with the idea that orange has to always be less than teal, we got to solve for t. We got to find the subscript of the first throwaway term. So that means that we're going to write the idea that will be the basis of our algebra will be that the maximum error, which we know is code language for the first throwaway term, has got to be less than the allowed error, which I've been color coding in teal. Now the maximum error is the absolute value of a sub t, using the a sub n formula where n is equal to t. So a sub t has got to be less than 0.02 in teal. Okay, what is a sub t? A sub t, well, if a sub n is 1/n, a sub t is going to be 1/t. So we need to find the smallest number t such that 1/t is less than 2/100. It's actually not too hard to do because if you multiply both sides by 100 and both sides by t, you get 100 is less than 2t. So that means 2t has got to be greater than 100. What is the smallest value of t that makes this expression true? Well, it can't be 50, because 2 times 50 is not greater than 100. What's the smallest value of t that makes this inequality true? Class? So that means the 51st term is the first throwaway term, which means k is always 1 less than that. We're going to keep terms n equals 1 through n equals 50. So that means when they say, how many terms are required? If we keep 50 terms, then we're guaranteed that our approximation will have an error of less than 0.02 from the truth. That is 50 terms. Basically, S sub 50 will be our approximation. Add up the first 50 terms. That's going to be the hardest part of the homework, is deciding how many terms you need to approximate the series. Let's do another example. Next page. And there's a definition of absolute and alternate convergence, which we'll get on block day. We just need to do another example here. Let's go to this one. So we worked with this a little bit. We know it converges. We did the alternating series test. So how many terms are required to approximate the series to within 1/1000th? Use your answer to write 4 things, sigma notation. Okay, so let's go through these. First of all, let's let a sub n equal, I just want to double check this. We're actually going to, yeah, that's actually my mistake. We're going to, unlike the alternating series test where a sub n is the non-alternating part, we're going to let a sub n represent the whole thing. We're going to let it represent -1 to the n. That's on the previous example also. That's why I had the absolute values there. So -1 to the n over n cubed minus 2. Okay, we have to write 3 let statements. First of all, the let statement for a sub n. Second of all, let t represents the subscript of the first, and what does t stand for? Throwaway, first term of the remainder, the first throwaway term, the first throwaway term. The book calls it, a throwaway is somewhat informal. The book calls it the first unused term. First term you don't use it. Basically, it's the first term that we throw away. And let K stands for kept. Let K represent the subscript of the last kept term. Those are our definitions. Now, we always start with the big idea. Our big idea comes from this diagram, and that is that our maximum error, which is code language for the first throwaway term, had better be less than the allowed error. So we're going to start with those words. We're going to say maximum error, we know has got to be less than the allowed error. That's our idea that drives us through the equation creation, the inequality creation, allowed error. Maximum error is always the first throwaway term. So it's the absolute value of a sub t. It's going to start out the same way every time. Absolute value a sub t is less than 1 in 1,000, 1 over 1,000. Okay? Now, a sub t, according to our definition, a sub t, the absolute value will wipe out the -1 to the n, right? Because the absolute value of -1 to the n is always 1. So it's basically going to be 1 over t cubed minus 2 has got to be less than 1 over 1,000. Multiply by 1,000 and multiply by t cubed minus 2. You don't have to worry about flipping the inequality because t is always going to be greater than 2. Hold on, t cubed minus 2. 8, yep, it'll always be positive. So we can say 1,000 is less than t cubed minus 2, which means I need to find the smallest value of t such that t cubed minus 2 is greater than 1,000. Now, it's not unreasonable to go to the calculator and use it as follows. On the calculator, I'm going to go to my y equals menu and type in x cubed minus 2. So x cubed minus 2 goes in for y1. I'm going to go to table set. I'm going to start it not at 0, but at 2. You start at 2, because that's the lower limit of summation. I'm going to go up by 1s, and then go to table, and I want to find the smallest number on this list that bumps the output over 1,000. That's my t value. According to the table, what is the value of t, class? Yeah, so I pull this in. The value of t, I'm going to be using that in the homework solutions, but it's clear from reading my calculator that t equals 11. And just to size this up a little bit here, put it right over here where I'm going to need it, I can tell from the table that t is equal to 11. Therefore, what's the value of k that we're going to use, class? Yeah, the last kept term is 10, but how many terms? See, we're going from 2 to 10. subtract and add 1. So there's 9 terms. The answer is you need the first 9 terms. You need the k equals 2 term, the k equals 3, or the n equals 2, n equals 3, all the way up to n equals 10. This is oh so easy to be off by 1. So that's why we need to carefully specify t, first throwaway term. I mean, do you agree that if we add up all the terms from n equals 2 to n equals 10, that will be 9 terms? If your English teacher says read chapters 10 through 20, how many chapters is that? It's 11 chapters. Chapters 10 through 20. You subtract and add 1. If you want to find the number of counting numbers in a list, you take the last number minus the first number and add 1. So 10 minus 2 is 8, plus 1 is 9. So there's 9 terms. So a sigma notation approximation. The answer number 1 would be the summation. We'll call it S is approximately summation from n equals 2 to 10 of negative 1 to the n over n cubed minus 2. And oh, by the way, then it says a decimal approximation. So a decimal approximation, let's write a home screen program for that. We've been doing home screen programs, and I want you to use a home screen program to get the decimal approximation. So go to your calculator now, and this will be all you need for the homework. As long as you can do a home screen program on the calculator, which we've been doing these for days now. Since n starts at 2, let's initialize n at 1. 1, store n, enter. Always initialize the value of the series at 0. And now here we go. Increment the value of n by 1. n plus 1 store n colon. Now let's bump up the value of the series. The series was s. We're going to add the nth term, which is negative 1 to the n over n cubed minus 2. Be careful how you type it in. It's negative 1 to the n divided by the quantity n cubed minus 2, close quantity. Store that in s, colon, and now display the ordered pair n comma s. We've been doing these for a while now with these pointy braces. Check this out. The second partial sum, basically when n equals 2, this is the first term. First term is that 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. I press to get this term. So there's the decimal approximation. This is the approximate value of the series. So if I pull, so now the answer to part 2 is, round into 3 decimal places, 0.138. I'm going to pull that into the notes so it'll get posted. But there's the home screen program. And there's a reason we've been learning these home screen programs. We started with Euler, and now we're doing home screen. The real reason we need them is for alternating series. That's where we really need the home screen program. Now, the only thing that's due tomorrow is a homework assignment, and I omitted problem 29. So you can cross problem 29 off. You'll see it on the homework solutions. It says omit. But this is really what you have to do on the homework. We'll see you tomorrow for block day, and we got the rest of the week to wrap up this unit. So thanks for coming. You are dismissed.